Now let's take a look at another example of LSTM. This time we're going to look at a sequence to sequence classification using LSTM. Alright, so right about here I am in my example page, and go ahead and select this one if you're already in the examples page. Alright, for me it's already selected, and I already have the code running on the browser. So if you are already here, so go here, and once you are inside, simply click on try example and try it on your browser. Alright, so I already have that running for me. There you go. So a quick walkthrough of the example itself and some idea about the data. So this is going to be a sequence to sequence classification. So this example talks about using the LSTM to make different predictions for each individual time step of the sequence data. So that's why it's sequence to sequence. So let's take a look at the data for a second, and then we'll come back to this sentence right about here. So this data contains 7 time series of sensor data, and this is obtained from the smartphone worn on the body. And each of these sequences has 3 features, and these features have varying length. These are basically your accelerometer values of different axes x, y, and z. So now we're gonna get an idea what's with the dataset. Now coming back here, which says making different predictions for each individual time step. So let's come to the graph here. So based on the acceleration, as you can see here, the sequence can be of different classes. So dancing, running, sitting, standing, and walking. So as the acceleration varies in different sequence times, the actual sequence of the output class also varies. So let's start from the top. First thing is to load your sequence data, and this is done here by calling load and the dataset's name. Variables are initialized for us, so here you are, xtrain is already initialized internally, and this is the output. Now if you do want to take a look at it, you can always call the display function and look at it. Now if you want to plot a graph with that information of xtrain and ytrain, which is basically the categories, then that graph would look something like this, which we already saw. Next is to define your LSTM architecture. So this one is pretty straightforward. So let's directly go to the layers here. First is the sequence input layer. Here you pass the feature dimension, which is your input dimension, and that is initialized right about here. So that becomes 3. Then you have the LSTM layer itself. Here you need to pass the number of hidden units, which is here 100, and the other arguments. Then you have a fully connected layer, and this needs to be the number of classes you need to predict, so that's going to be 5. Then you have a softmax layer, that'll be your classification layer. All right, next is you set the options. So you call options, and then you can pass these different arguments. So you can choose Atom or some other optimizer. I have added this line, which is the max epochs of 5, to reduce the time it takes to train. Since we're running on the browser, if it takes too long, then it'll time out and then you won't be able to see the result. And I made it 5. Since that is 5, we can drop the learning rate after 3 epochs. Of course, this is just for the sample, and this is not a very good experiment to learn the dropping rate since we're only running for 5 epochs. Okay, so you can also pass the initial learning rate right about here, 0.01. You can change that as well if you like, and the other arguments as well. All right, so next is you actually call the train network function. You pass the data, labels, the layers, and the options, and you store everything in the variable net. And then finally your graph will look something like this. This is for 30 epochs, as you can see here, but we're only going to run for 5 epochs. Okay, so after 30 epochs, so here they want to first look at how the test data looks like. So you basically plot the x test moisture features. This is how your test data looks like. Now what you want to do is you want to make that prediction on the x test data. So you call the function classify, you pass your net information of your training, and you also pass the data of the testing data set, and then you store all the results to ypredict, and then the accuracy is calculated simply by this mathematics here, and there you go. That's your accuracy, which is 0.9959, which is pretty good. So this is run for 30 epochs, and that is the accuracy. And then you're plotting the y prediction and the y test. So when you do that, this is how it looks like. So if you see, there is an overlap with the predicted and the test. Pretty good actually. So this may not look like this when you only run this for 5 epochs. So that's also a good example to verify how this works when the number of epochs are less. Alright, so pretty straightforward actually. And let's go and run this. So this might take some time. So let's say about 3 to 5 minutes. So I'll get back to you in that time. So I'm going to say run all and then sit back. So there you go, it started. It goes through all of these pretty fast, and then finally it stays on the training itself for a while. Alright, so the experiment is complete, as you can see here, and let's take a look at it. So I'm going to directly go to the graph here, and there you are. So 5 epochs, learning rate is 0.001. That is the endpoint, and we have an accuracy not pretty good, so that's roughly about 50%. So that's not good at all. And let's take a look at the accuracy when you compare the results, and this is only about 79%, which is not bad, but of course comparatively it is not good. So this is the plot with the predicted and test. So as you can see, towards the end it is not quite matching. Alright, so this is a straightforward example of sequence to sequence classification with LSTM. So go ahead and try back with different epochs and different learning rates and see if you can match it. Of course, you can also add many LSTM layers. You can also increase the number of hidden units and so on. Great, really good stuff. And now we have some exposure to the RNN and the LSTM variation especially. Awesome, good job.